This video is on stoichiometry. I will define stoichiometry here in a moment. First, we're going to talk about what mole ratios are in a balanced chemical reaction or equation. We're going to talk about how to make conversions from moles of one thing to moles of another using a balanced chemical equation. And then we are going to move on to how to make conversions from the mass of something to the number of moles of something using a balanced chemical equation. So I'm sure you've heard me say that chemical equations are nothing but a recipe. So let's start out with one that's something that's familiar with you. So here is a recipe for producing pancakes. So everything on the left, your ingredients in this chemical reaction, are your reactants, and everything on the right of the arrow are your products. So we have 4 reactants and 1 product in this reaction. So what's missing? If you said that what was missing are quantities, you are correct. So let's go ahead and fill in the quantities for all of our reactants and our products. So I went ahead and I filled in the quantities for everything. And now we can look at ratios between all of the reactants and the products. So we're not going to write all the ratios, we're just going to write some of them. So for example, if I asked you to write the ratio of flour to pancakes, you would say that you would need 2 cups of flour to make 5 pancakes. You could do the same for, I don't know, flour to oil. So we can say we need 2 cups of flour for every 2 tablespoons of oil. Of course, you can reduce that to a 1:1 ratio if you wanted to. Or how about your ratio of eggs to pancakes? So I can make 5 pancakes with 1 egg. Well, if I have 1 egg and everything else, I can make 5 pancakes. So I could do this for every single one of these reactants. I could write ratios between the reactants, and I can write ratios between the product and the reactants. But the point is that I can write ratios. And I can then use those ratios to now as conversion factors. So what do I mean by as conversion factors? So let's say I don't want to make 5 pancakes. I only want to make 3 pancakes because 5 just seems like way too many. So I can go and adjust my recipe so that I will yield 3 pancakes as opposed to 5 because I have a recipe with ratios between the reactants and the products. So I could set up a little math equation. So I want 3 pancakes. This is what I am given. I want to make 3 pancakes. And I know that according to my recipe, that it is, if I want to know how much flour that's going to take, it takes 2 cups of flour to make 5 pancakes. So if I were to work out this equation, your pancakes cancel. You would be left with flour. You would be left with 1.2 cups of flour. If I only want to make 3 pancakes, instead of needing 2 cups of flour, I would need 1.2 cups. And I know this because I have quantities in front of my reactants, quantities in front of my products, and I can find out the ratios between the two so that I can adjust my recipe. What you have just done is you have done some stoichiometry. So stoichiometry's definition is to calculate or calculating relative quantities of reactants and products in a chemical reaction. You just did that. You used this relative quantities of flour to pancakes from your chemical reaction up here to determine how much flour you would need if you only wanted to make 3 pancakes. So let's do some more stoichiometry with this reaction. All right, so let's use our balanced chemical equation or our recipe up here to determine how much oil we would need if I only had half of a tablespoon of sugar. So let's say I started out, I went to my cupboard and I noticed that I only had half a tablespoon of sugar. And I still wanted to make pancakes for myself because I really want pancakes. So I need to figure out how much of everything I'm going to need. So we'll start with the oil. So from our ratios in our chemical equation up here, we know that for every 1 tablespoon of sugar, we would need 2 tablespoons of oil. So we can do the math on this, and we would get that we need 1 tablespoon of oil. So if I was going to do, I could do the same for all of my ingredients, adjusting my recipe for the amount of sugar that I actually have as opposed to what it calls for in the recipe. That's just stoichiometry. Okay, so let's apply what you just learned with an actual chemical reaction. Not that cooking's not a chemical reaction, it is, but with a chemical equation such as the chemical equation for the production of NH3. NH3 is ammonia. This chemical equation is really just the recipe for making ammonia for fertilizers. In case you're wondering, this is actually something they do in industry to create fertilizer, that you would put on your grass or your plants. You'll notice from our balanced chemical equation that you need 3 H2 to 1 N2, and that'll yield 2 NH3. Now, the beauty of a chemical equation versus, say, a food recipe is that your quantities that are out front. In a food recipe, those quantities are in a bunch of different units, cups, tablespoons, teaspoons, whereas in a chemical equation, your coefficients, and of course we can assume that there's a 1 right here, your coefficients are all in the same unit. So we're not all over the place with 1 meaning cups and 1 meaning tablespoons and 1 meaning teaspoons. And those units are usually moles. That's how you like to read those coefficients are mole quantities. So 3 moles of H2, 1 mole of N2, and 2 moles of NH3. They can also be molecules, but when you're actually doing a chemical reaction, you're not measuring out like 3 molecules of H2. It would be impossible to actually just get 3 molecules of H2. You would actually think of that as being 3 moles. So from our balanced recipe here for making NH3, we can come up with ratios or conversion factors that we can use if we decide to change any of these quantities. So I just picked a couple. Let's find the ratio between H2 and N2. So that ratio is 3 moles of H2 for every 1 mole of N2 are required for this reaction. What about our ratio of N2 to NH3? So this recipe requires a 1 to 2 ratio of N2 to NH3. So because we have these ratios, if we were to change any of these quantities, so if I decided that I didn't want to use 3 moles of H2, I wanted to use 20 moles of H2, then I could use the relationship from this equation or the ratios from this equation to determine how much N2 or NH3 would result from this reaction. These, by the way, are called mole ratios, and you need to know how to write mole ratios. Now, I'm going to be nice about mole ratios in that if they can be reduced and you don't reduce them, I'm not going to be that upset about it. So if you have a 2 to 2 ratio and you don't reduce them to 1 to 1, I don't care. I just want you to be able to look at your balanced equation and write mole ratios between your reactants and your products, or your 2 reactants, or if you had 2 products, your products. I just want you to be able to do that. Here's an example of a question that I could ask you to solve using mole ratios from a balanced chemical equation. So I want to know how many moles of N2 are needed to produce 13 moles of NH3. So here's what we want, and here's what we're given. So we're going to start with what we were given. We want to take 13 moles of NH3 and convert it or determine the amount of N2 required. So we're going to use our balanced equation up here and the mole ratios between NH3 and N2 from this equation to convert 13 moles of NH3 to moles of N2. So in our equation, it tells us that it requires 1 mole of N2 to produce 2 moles of NH3, and that ratio should be true. with this 13 moles. There still should be a 1 mole of N2 to 2 moles of NH3 ratio when we're done. So we do the math here. 13 times 1 divided by 2 is 6.5 moles of N2. And you'll notice that our ratio from our recipe is a mole of N2 to 2 moles of NH3, and that ratio still holds true. We just changed the quantities, but we still have a 1 to 2 ratio between N2 and NH3. Okay, let's do another example. So same equation, we're using the H2N2 and NH3 equation. How many moles of H2 would be required to react with 2.6 moles of N2? So we want moles of H2, and we were given moles of N2. So we start with what we were given, 2.6 moles of N2, and we are trying to convert that or turn that into a number of moles of H2, which means that we want to get rid of moles of N2, so we're going to put that on the bottom. And then the numbers we put here are the numbers from our equation up here. So the ratio is 3 moles of N2 for every 1 mole, 3 moles of H2 for every 1 mole of N2. So if we have 2.6 moles of N2 and we want to keep that ratio, we're going to go ahead and multiply across and divide by what's on the bottom. And you end up with 7.8 moles of H2 being required to react with 2.6 moles of N2. And you'll notice that our 3 moles of H2 to 1 mole of N2 ratio from our equation still holds true. 2.6 moles of N2 and 7.8 moles of H2, if you divide 2.6 into 7.8, you get 3 to 1 ratio. All right, let's do a little bit more, but this time we're going to use a different equation. So this is the equation for the combustion of propane. You may have heard of propane, at least I hope you've heard of propane. It's the stuff that's in those tanks that are in your grills that you use in the summer. So this is whenever you light the propane gas, you're igniting it, reacting with oxygen and producing carbon dioxide and water. So this is a combustion of propane reaction. So let's do some stoichiometry around propane. So let's say you had a backyard barbecue this summer and you noticed that when you were done, you had consumed or used 52 moles of propane. So 52 moles of propane is used, and you want to know how much carbon dioxide did I produce in this reaction. You might want to consider that, just considering the fact that carbon dioxide is a greenhouse gas. And so it's something that, goes into the atmosphere, gets up into our upper atmosphere and kind of creates a little tent that makes it difficult for the heat of the earth to escape. So, people are concerned about greenhouse gases and their effect on our environment. And so, how clean burning is propane really just means how much carbon dioxide is it producing? Is it producing a lot per mole of carbon or per mole of propane, or very little? So let's find out how much carbon dioxide we produced when we had our backyard barbecue. So what we were given was that we had 52 moles of propane. So that's where we're going to start, is with our 52 moles of propane. And what we're asked to find from that is moles of carbon dioxide. So that's going to go on the top. And of course, moles of propane will go on the bottom. So we're going to use the ratios from our equation between propane and carbon dioxide. So we know that for every mole, 1 mole of propane will produce 3 moles of carbon dioxide. So we're going to fill that in. There's 3 moles of carbon dioxide produced for every 1 mole of propane. And so how much carbon dioxide would be produced from 52 moles of propane? So if we do this little math equation, 52 times 3 is 156 moles of carbon dioxide produced from our backyard barbecue. So I'm going to have you try one. So you try this one. So I want you to read the question, pause the video, work it out, and see if you get the same answer that I do. So in this one, it's how many moles of oxygen are you going to use if you produce 16.2 moles of H2O? So pause the video now. All right, so you have or are given 16.2 moles of H2O. You're trying to convert it to moles of O2 from moles of H2O. So you set up your ratio. It's 5 moles of O2 for every 4 moles of H2O. And if you do the math on this, you get 20.25 moles of oxygen are used when you are producing 5 moles of 16.2 moles of H2O from this recipe or equation above. All right, and last but not least, we're going to talk about extending this a little bit into mass to mole calculations. So what we've been doing are mole to mole calculations, where I give you a mole quantity of one thing and ask you to find the mole quantity of the other. But the fact is, in real life, you don't go back into a lab and really measure things out in moles. What you measure them out in is grams. And so let's try some more, just a slight bit more complicated ones where instead of starting with a mole quantity, we're going to start with a mass quantity. So in this question, I'm asking you how many moles of C3H8 are burned, so consumed or used up, when you burn 64.1 grams of oxygen. Now you've got to be careful, and first of all notice that I gave you grams of oxygen, not moles of oxygen. And you need to realize that this number is a mole quantity, not a gram quantity. So your equation's written in terms of moles, but I've given you an amount of O2 in terms of grams. So be very careful when you're doing these calculations that you notice that I've given you a quantity in grams, and that quantity is not the same unit as what your equation is written in. Remember, your equation's written in moles. So what that means is our number that we started with, our 64.1 grams of oxygen, needs to be converted to moles first. So if you convert it to moles, then you can use your mole ratios to convert it to moles of C3H8. So then you can go to moles of C3H8 from there. So you've got to turn the grams into moles to be able to compare it to your balanced chemical equation, because it's written in mole quantities. So how do we go about doing that? You should already know this. How do we go about converting a number of grams of something into a number of moles of something? So what do you need to do that? And if you remembered that you need molar mass to do that, you are in good shape. So if I know the molar mass of O2, I can convert the grams of oxygen to moles. And then once I know the moles of oxygen, I can turn that into or determine moles of C3H8 using the mole ratio from the equation. So let's do that. So we'll start with our 64.1 grams of oxygen. And we're going to do two conversions here. The first thing we're going to do is we're going to convert grams of oxygen into moles of oxygen. So we're going to need to add up the molar mass of O2. So I just did that, and O2's molar mass, 1 mole of O2, weighs 31.998 grams. Okay, so once we've done that, that means we've converted grams into moles of oxygen. Now that we have this in the same, term as our equation's written in, which is moles, then we can go ahead and use our mole ratio to determine how many moles of C3H8 we would need to react with our moles of O2. So you put C3H8 on the top because that's what you want to be left with, and of course moles of oxygen goes on the bottom over here so that it can cancel out. And then we need to just look up the numbers to plug in here from our balanced equation. So you'll notice it's 1 mole of C3H8 for every 5 moles of oxygen according to our equation or our little recipe. So it becomes a matter now of just doing the math across. So 64.1 times 1 times 1, and then divided by 5 times 31.998. And when you do that, you get 0.4006, so 0.401 moles of C3H8. So in this question, it was a little bit more complicated because we had to take this little extra step to get it into to get oxygen into moles before we could do the equation we did before. But not that much harder because you should already know how to do this from the last unit. So I know this is getting a little lengthy, but we're going to do one more. Actually, you're going to do this one. So how many moles of CO2 are produced when 15 grams of H2O are also produced? So we know that when there are 4 moles of water produced, 3 moles of carbon dioxide are also produced at the same time. So we can use that ratio. The issue is those are moles, remember? And we're given 15 grams of water. So pause the video, work this out. It's very similar to the one we just did, and see what answer you get. All right, so let's look at how we set this up. So we started with what we were given, which was our 15.6 grams of water. And to convert our 15.6 grams of water to moles so that it's in the same terms that our equation is written in, we use the molar mass of water, which is 18.015 grams. So that gets us to moles of water, and then we can use our mole ratio from our equation between CO2 and water to turn moles of water into moles of CO2, and we end up with 0.624 moles of CO2 being produced at the same time that 15 grams of water is produced.